Welcome dear students. Now we are going to discuss another type of the isomerism, that is the metamerism. We have already discussed what is isomerism and structural isomerism and different types of the structural isomerism like position isomerism, functional group isomerism, chain isomerism and ring chain isomerism. We have already discussed all these types. Now the next one, that is metamerism. Let us first talk about the introduction of the Metamerism. So, students keep in mind that in 1831, when John Jacobs Berzelius studied some compounds that had same percentage composition but different properties, he named those compounds metamers of each other, because in 1831 there was no term like isomerism, and in all the publications of the IUPAC even the isomerism term was not used, rather metamerism was used, and those compounds that had same chemical composition but different properties, they were used to be called as the metamers. They were not called as the isomers because the term isomerism was not yet coined. So metamerism was a substitute for the term isomerism. Then later on, when this concept it gained very vast, it became very vast. When different type of the isomerism were studied, then metamerism became one of the subtype of the structural isomerism and a term with a larger perspective that was introduced, and that is now called as the isomerism. So once isomerism was called as the metamerism and isomers were used to be called as the metamers. Now let us talk about the definition of metamerism. Dear students, metamerism is the type of the isomerism in which compounds which are called as metamers, they have same molecular formula. When they have same molecular formula, it means their percentage composition that will also be same, but they have different alkyl groups on both sides of same functional group. So they have same molecular formula, they have same composition, but they have different alkyl groups. You have already a concept of the alkyl groups, that what are the alkyl groups. They have different alkyl groups on both sides of the same functional group. It means metamers, they have same functional group. If they have same functional group, then dear students, they will be belonging to the same homologous series. And if they belong to the same homologous series, it means that they will be having same methods of preparation, very much similar chemical properties, but they differ in their physical properties, because physical properties, they largely depend on the molecular mass and the arrangement of the atoms in the compounds, which is, if different in them, then the physical properties will be different. But if they have same molecular formula, it means their molecular mass or molar mass that will be same, then the physical properties will be different due to the different arrangement of the atoms. Now next is, do all classes of the organic compounds they show metamerism? No, it's not like that. So there is some condition to show isomerism. All the classes of the organic compounds, they do not show isomerism. Now, what is the condition? The first one is that functional group must be non-terminal. Non-terminal mean that there should be carbon chain on both sides of the functional group. Just like you can see that in case of aldehydes, in case of alcohols, in case of thiols, they have terminal functional groups. There is only carbon chain on one side of the functional group, just like this one, this one. They have only carbon chain on one side of the functional group, so they are called as the terminal functional groups. If a class of organic compound has terminal functional groups, then they cannot show metamerism. So the first condition is that there should be carbon chain on both sides of the functional group. The second, alkyl group must be attached to some divalent or polyvalent heteroatom. So there must be some divalent or polyvalent heteroatom in the functional group, and that should be surrounded by the alkyl groups. Just like in case of ketones, you know, I will take example of the simplest ketone, acetone. The functional group is non-terminal, as you can see that there are two carbon chains on both sides of the functional group. But in this particular group, none of the alkyl groups is attached to some atom that should be divalent or polyvalent, and it should be heteroatom. You know, in organic chemistry, heteroatom means some atom other than carbon. So the alkyl groups are present on both sides of the functional group, but none of the alkyl groups is attached to the divalent or polyvalent heteroatom. Heteroatom means some atom other than carbon. That heteroatom may be oxygen, nitrogen, sulfur, etc. So the alkyl groups, they must be attached to some divalent or polyvalent heteroatom. So that's why ketones will not show metamerism even though there are carbon chains on both sides of the functional group, but the alkyl groups are not attached to some heteroatom. Both are attached to the carbon. So what are the classes that show the metamerism then? Dear students, ethers, sulfanes, sulfoethers they are called as, and you can say secondary and tertiary amines or amides, and similarly acid anhydrides. They show the metamerism. Ethers, they have heteroatom oxygen, and both alkyl groups are attached to that heteroatom. Sulfanes have heteroatom sulfur, and both alkyl groups are directly attached to that sulfur. Secondary and tertiary amines, they have nitrogen. It is a polyvalent, trivalent heteroatom. And similarly in case of amides, and in acid anhydrides, alkyl group is attached to the divalent oxygen atom. Now let us take some examples of the metamers. The first one from the class of ethers, like methyl propyl ether. It has methyl group and propyl group, so it will be called as the methyl propyl ether or methoxypropane. And the second one is diethyl ether. Ethoxyethane is the IUPAC of name of this compound. So they are the metamers of the each other. You can see that the functional group is non-terminal. It is present inside the chain and the carbon chains are present on both sides. And similarly, the alkyl groups are also attached to a divalent heteroatom, which is oxygen here. So they are having same number of carbon, hydrogen and oxygen atoms, but they are having different alkyl groups on two sides of the functional group. In one case, that is methyl and propyl. In the second case, two ethyl groups are attached on the either side. So these two compounds, they will be called as the metamers of each other, and they will belong to the class of the ethers. Now, what are the sulfanes? They have only sulfur atom instead of oxygen. So, dear students, if I will replace this oxygen with sulfur, then they will belong to the class of the sulfanes, and that will be the methyl propyl sulfane, and it will be the diethyl sulfane, and they will also be the metamers of the each other. Now let us talk about the amines, secondary amines first of all. Just like a very simple example, instead of sulfur, now place NH. They are two secondary amines. Why they are secondary amines? Because nitrogen is attached to the two alkyl groups, two carbon atoms. And again, you can see that this one is the secondary amine functional group, and on both sides of the secondary amine functional group, again the nature of the alkyl groups, that is the different. So they will also be called as the metamers of each other. This one is very simple. It will be called as the diethylamine, and that will be called as the N-methyl propane 1 amine, or you can say that will be the methyl propyl amine. So they will also be called as the metamers of the each other. Now if we talk about the tertiary amines, what will be the example from the tertiary amines? Then you are required to do nothing, just replace the hydrogen with methyl and this hydrogen with you can say replace it with methyl, or even you can replace it with propyl. So they will also be having the different functional groups, different alkyl groups attached to the nitrogen atom. So they will also be called as the metamers of the each other. Now let us take some example from the acid anhydride. You are well aware of this, that it is ethyl acetate. So this one is the ethyl acetate, and similarly this one is methyl propionate. This one is ethyl acetate and this one is methyl propionate. So you can see that again there are different alkyl groups which are attached to the non-terminal functional group having a divalent heteroatom, which is oxygen. So these are two anhydrides and they will be considered as the metamers of the each other. Now the last one, that is from amides. Simply replace this with NH. Now this will become an amide because this is the functional group amide, and again you can see that there are different alkyl groups on both sides of the amide functional group, so they will be called as the metamers of the each other. So metamers are basically those isomers which have same chemical composition, same molecular formula, same molecular weight, but they have different alkyl groups on both sides of the functional group. And the condition is that the functional group must be non-terminal and it must have some divalent or polyvalent heteroatom. And all the classes of organic compounds, they do not show metamerism, rather ether, sulfane, secondary tertiary amines, secondary tertiary amides, and similarly acid and hydrides. These are the major classes which show the metamers. And I have given example almost from each of the following categories that show the metamerism. So this was all about the metamerism. Next time we will come up with the tautomerism. Till then, take care.